Good morning, class, and welcome to this lesson on Magnetism 8, magnetic fields in a loop of wire. Okay. Today we will be able to identify the direction of the magnetic field in a circular loop of wire. Okay, so as you can see here, we have a battery. It's connected to a wire, so there's a current in the wire. And we know from before that if we have a wire, we know there's going to be a magnetic field around the wire. Okay, this is a magnetic field going around the wire, and that is dictated by right-hand rule number 2. So for example, in this particular wire I drew, the current would be going up. Because my fingers curl around this way, that means my thumb's going to be pointing upward. So what if I take this wire right here and I bend it into a circle? Well, I have a circular loop of wire. I'm going to use the same right-hand rule number 2. And all you have to do is find the direction of current, and then your thumb will follow the direction of current. And when you curl your fingers around, your fingers point like the magnetic field does. Okay? So your fingers point in this direction. So what we have here is basically a loop of wire is just like a bar magnet. It has a north and south pole. Remember, in a bar magnet, we know our field lines point from north to south. Our field lines point from north to south. Well, when we do the right-hand rule, we take our thumb, we put it around the loop in the direction of current, we bend our fingers in, and whatever direction our fingers are pointing, that's like the north side of the magnet, and this is the south side of the magnet here. Okay, so it's pointing towards the north side, and so these arrows follow in the same direction as your fingers. So your fingers point to the north, and then the field lines point from north to south. So a loop of wire with a current works just like a bar magnet. The bar magnet is not actually there, that's why it says phantom bar magnet, but it works exactly the same way. And so we have an equation for this, and it's going to look very familiar. Remember, in a single wire with a current, our equation was B equals the permittivity of free space times the current over 2 pi r. Okay, that was our formula before, with r being the radius away from the wire. Now we're going to modify that just a little bit. Our magnetic field is going to be the N, I'll get that in a second, times the permittivity of free space times the current. So this is the exact same, you can see. And on the bottom, which is going to be 2, and we're going to do capital R. Capital R being the radius of the circle. Capital R being the radius of the circle. And N is the number of turns. Number of turns or loops. Number of turns or loops. Okay, so it looks almost exactly the same. So we can figure out the magnetic field in this particular circular loop here based off, this is a constant, the current, and then the radius from the center of the loop, and the number of turns or loops. In this one, the number of turns is 1. It's 1 loop. Because what we have found, this is going to lead to my next thing here. What we have found is, I'll come back to that in a second. Too, is that if you have what's called a solenoid is nothing more than a circular loop of wire looped over and over and over and over again. Every single time there's a loop, it's like saying if the magnetic field is equal to epsilon naught I over 2r, that is the magnetic field. Every single loop adds on to that. And so every time you add a loop, you're adding the magnetic field again and again and again. It's the whole concept of is it easier to break one twig, or is it easy to break a bundle of twigs? And as you know, it's very difficult to break a bundle of twigs because while one twig may be weak, all of them put together are very strong because they all add up. Same thing here. The magnetic field from one loop of wire may not be that much, but when you add them all together, when we add the field over and over and over again, then you get this. Then you get a very strong magnetic field. And this picture right here, basically they took this solenoid and they cut it in half. They cut it in half right along this line right here. Okay, and so this is the solenoid right here, showing you the bar magnet inside. Okay, so let's go back here a second. If we have two loops going in the same direction, if we have two loops going in the same direction, that is like having a north and south pole end to end, and so they're going to be attracted. And if we have two loops going in opposite directions, they'll be repelled, because if we have opposite directions, then it's like having the same pole to the same pole, south to south and north to north. Okay, so that's just a quick one, and I'm going to show you an example of kind of a typical example of a question like this. So we have a wire and a loop. Both have a current. These are separate. Okay, there's one wire here, loop here. And this one has a current going down, this one has a current going in a clockwise direction. And the question is, at point C, what is the magnetic field? What is the magnetic field at point C? Okay, well, if we do right-hand rule number 2 on this wire right here, we would take our thumb and point it down. Our fingers would curl around, and at point C, our fingers would be pointing up. Okay, so this is the magnetic field due to wire 1. On this current here, we would take our thumb and put it along this, and then we would curl our fingers down, and at point C, it'd be facing down. So in order to find the magnetic field at point C, we would have to do the magnetic field equals epsilon naught I over 2 pi r. This is from excuse me, B1. This is from the first wire here. Okay, and then we are going to minus. We're going to minus this one because they're in opposite directions. So it would be minus n epsilon naught I over 2 r, r being the radius here. Okay, so that's just one example of many of where you might see a loop of wire in comparison with a regular wire, and how we find magnetic fields. Okay, so that is it. Just remember that you are still using right-hand rule number 2, and instead of your fingers curl around, and wherever they meet the plane of the circle is what the direction of the magnetic field is going to be.